Hi, this is part 8 of model building outline, and in fact the last video of this course and this outline as well. So let's get started. The skills we will cover in today's lecture is about SVM, which is the last algorithm we will study in this outline. We will also see the working of SVM, and in the last we will see the evaluation of support vector machines. So let's get started. What is actually SVM in R? Support vector machines, or SVM, is a type of machine learning algorithm that is used for classification and regression analysis. It is particularly well suited for solving problems involving large datasets or high-dimensional feature spaces. The basic idea behind SVM is to find the best separating hyperplane between the classes in the data, which is called the maximum margin classifier. The hyperplane is determined based on the support vectors, which are the data points closest to the hyperplane. The goal of SVM is to maximize the margin between the classes, which leads to a more robust and accurate model. SVM can handle nonlinear data by transforming the data into a higher dimensional space and finding the best hyperplane in that space. SVM has been widely used in various applications such as image classification, natural language processing, and bioinformatics. So what are the advantages of using a support vector machine? SVMs are effective in high-dimensional spaces. They can handle a large number of features and still produce accurate results, which means that you can pass more independent variables or columns. SVMs are effective in handling imbalanced datasets, where one class is significantly larger than the other. SVMs have a solid mathematical foundation and are guaranteed to find the global optimum solution. SVMs are also robust to outliers and are able to identify observations that are significantly different from the rest of the data. Now here are also some disadvantages of using SVM. Let's see. Like any other machine learning model, SVMs can overfit the data. Now, if you want to do hyperparameter tuning of your model, then SVMs require careful tuning of several hyperparameters in order to work correctly. SVMs require a large amount of memory to store the training data and the model parameters. They are also primarily used for binary classification problems where the goal is to predict one of two classes. Unlike other algorithms such as logistic regression, SVMs do not provide a probabilistic interpretation of the model predictions. So here's how it works. The first step is to prepare the data by normalizing the features and splitting the data into training and testing sets. The next step is to construct the optimization problem, which involves finding the best hyperplane that maximizes the margin while correctly classifying the data. Then the optimization problem is solved. The solution to this problem determines the support vectors, which define the boundary between the classes. For nonlinear data, SVM transforms the data into a high-dimensional space using a kernel function. In this space, it's possible to find a linear hyperplane that separates the classes. You can also use other functions. In the last, once the model is trained, it can be used to make predictions on new data. The prediction is based on the position of the new data relative to the hyperplane. So let's see the syntax for SVM. Here's an example of the syntax for using support vector machines in R for a binary classification problem. Just use the SVM keyword, pass some parameters such as dependent and independent variables, then dataset, then the kernel, and then the last cost. Now it's time for a hands-on session. Let's move to our studio. So first of all, I will load the required packages by saying library, CA tools, and then I will read the head of my data frame. So here I have a dataset with the name of ADV data frame 2 that has 4 columns. At first, I will split the dataset into training and testing parts. I will say sample dot split, and here I will pass the data frame, and I will say the split ratio should be 0.8. That means 80% of the dataset will be used for training. Now here I say train ADV, and here I say subset. I pass the data frame, and then I say split equals to true. And similarly, I say test ADV, and here I say subset. I pass the data frame, and the split equals to false. All right. Now here I have to load one more library, which is E1071. All right. Now here I will create the SVM model, and I will use the function of SVM, and here I will say I want to predict the column of purchased and take all the rest of the columns for prediction, and I will say take the data of train ADV, and the type should be the classification, and here I say kernel equals to linear, and here let's say, and here I will say Part8, and I will use the predict function, and here I will pass my model, SVM model, and I will say do the prediction on test ADV except the last one, and here I will say Part8 to see the values. Now let's run it. You can see prediction for each of the values. The 0 represents that the user has not purchased, and the 1 represents that yes, the user has purchased. Now let's say I want to see the summary of my SVM model. Then I can say summary SVM model. It shows the number of support vectors, the number of classes, and so on. Let's say if I want to assess the performance of my model, then I can also make a confusion matrix. Now here, let's see test ADV. All right, and here I will pass the Part8. All right, so you can see that there were 241 right predictions for the purchase of 0, and the wrong were 48. And for the 1, there were 95 correct predictions and 16 wrong predictions. So that means that there is a little error in your model. Now let's move forward. Let's say head, and we have a data set of iris, and we want to predict the species with the help of these columns. Now let's move forward. First of all, I will install the required packages. I will say install.packages and ggr, and I will say install.packages, and here I will say reshape. Let's install them. The package is being downloaded. All right. Now let's load these packages. All right. Here I will say library and reshape library caret. All right. Now, first of all, I will create a variable with the name of partition, and I will use the function of create data partition for splitting the data set into training and testing parts. And here I will say iris and the species data set, and the p value should be 0.8 and list equals to false. Now similarly, here I will say train iris and I will say partition, and here I will say iris and partition, and here I will say test iris and take the iris dataset and don't take the partition. All right. Now, in order to feed our machine learning model a good data, we first have to clean the data sets. Now we know that in the simple width column of iris dataset, there are outliers because we have previously made a box plot and a scatter plot to see the outliers. Now, in order to remove the outliers, first of all, we have to find out the quantile. In order to do that, we first of all say quantile, my quantile, and here I will use the quantile function. Here I will say train iris, and the column name is super width that have outliers. And here I say probes equals to, I will use the combine function, and here I will say 0.25, and here I will say 0.75, and na.rm equals to false. Great. And here I find the interquantile range. I use the function of IQR and I say train iris, and I pass the data set of super weight, and here I say the upper boundary is my quantile 2 plus 1.5 times IQR. And similarly, I will say lower boundary equals to my quantile 1 minus 1.5 times IQR. Now here I will say normal iris, which means that the normal iris dataset that is clean of outliers must have this train iris dataset values of super dot weight greater than lower boundary, and the train iris super dot weight should have observations smaller than upper boundary. And before that, I pass the train iris dataset here. Now here I do the cross validation. Before making the model, I will say train control And here I pass the method equals to CV, and I say save predictions equals to true, and number equals to 10. All right. And here now I create my model. I say SVM model 2, and inside this model, I use the train function, and inside this function, I say I want to predict species and take all of the variables for prediction. And here I say method equals to SVM radium. All right, and brain control equals to CV, and data equals to grain iris. And in the last, I pass the metric equals to accuracy. All right. Here I will print the model at first. I'll say print SV model 2. And we can also make predictions. I say yprint 2, and I use the predict function. I say take the SVM model 2 and take the test iris dataset. And similarly, if I want to make a confusion matrix of my model, I say CM2, and I say confusion matrix. And after using this function, I pass the yprint 2. All right, and then I say take the test iris dataset and the variable of species. And here I just print CM2. Now let's run this whole chunk of code. Great. So first of all, you can see the model here with 120 samples for predictors and 3 classes. And this is the accuracy for each of the class. And here's the confusion matrix. You can see there were 9 correct predictions for Sedosa and 1 was wrong. And all of the predictions for Versicolor and Virginica were right. And the accuracy of the whole model is 0.96. And this is the detail. This is the balanced accuracy for each of the class, sensitivity, specificity, and these are all other important details. Now let's get back to slides. So here's what we have learned today. Now this is your homework. Just click on the link of the dataset, clean the dataset, build a support vector machine, and do the evaluation of support vector machine. Now, this is the end of this course. Good luck. See you next time.